Hi folks, I'm Tim Bannister and I'm going to talk about serverless PCI compliance on AWS. Let's talk about some backstory. In this talk I'm going to talk around the example of an app that you might use for ordering drinks or in a bar or cafe, kind of topical in the years 2020 or 2021. And let's say that you've been asked to add card payments to that app. Maybe it's for the waiting staff to handle card payments, or maybe it's for the customers. And the merchants, that's the bars that are going to be picking this app to use or this website, they're aware that they need to ask you for PCI-DSS paperwork. And so this talk is about making that journey easy for you on AWS. The two most important words to make that journey easier are not applicable. The strongest piece of advice that I want to give you is to make as much as possible as out of scope, things that you don't need to do at all, take them out of scope and leave them there. In the rest of this talk, I'll hope you learn some ideas for that. I'm specifically talking about Amazon Web Services because this talk is for the Community Summit, because personally I'm most familiar with Amazon Web Services, and because actually, because of its partnership with a very large retail platform, I believe that Amazon Web Services is a really good fit for retail needs. Some things I'm not going to cover. I'm not going to really talk about CI and CD. I'm not going to talk about how you check your code or get it approved. You can actually use Amazon Web Services, Code Pipeline and family, which are a good choice for high assurance workloads, but that is really another talk. Let's talk about some of the terms that I'm going to use. I've already mentioned merchants. There is some jargon that might come up, don't worry, then there's no quiz, and I will recap these if they become relevant. So if you're a PCI-DSS service provider in the cloud, that means that you're probably offering software as a service, and your customers are probably what PCI-DSS calls merchants. The thing you secure is a cardholder data environment. Now, merchants might ask you for an attestation of compliance, and what that means is that they don't want to scrutinize your systems directly. What you don't want to do is that every time you onboard a new customer, they go through the same paperwork checking that you've secured things. Instead, you want to say that here's a form, you've shown that you're compliant, and your customer, the bar or the cafe, can use that. And to get you that piece of paper, here's what PCI-DSS asks for. There's 12 main points, and then the standard dives into these, some in quite a bit of detail. There's plenty of requirements, and each of these requires at least some evidence for getting the attestation of compliance. They want not just that you're doing it, they want to see that you're doing it. The origins of this standard, largely predate cloud computing, but they don't predate online shopping and the web. But it's from a slightly different era of IT. Unlike what I'm going to compare it to, which is Amazon Web Services' well-architected framework. Now, I like this framework because the pillars are dividing up how you think about an architecture, and actually for identifying the considerations that you're not covering in a particular theme. So this talk focuses on security. And so AWS tells you that you should implement a strong identity foundation, that you should enable traceability, and so on. In our view, my view at the Scale Factory view as well, these AWS principles are actually a really good fit for PCI-DSS in the cloud. PCI-DSS's own words that you should protect systems and networks and be prepared to respond to a system breach. Not hugely different. Two that I want to emphasize: keep people away from data, automate security best practices. Keep those in mind when you're designing your compliant-oriented workload, and you will have an easier time of it. You also want to build on some secure foundations. So my advice, if you want to achieve compliance, is to use AWS managed services that help you cross off these requirements. The easiest win is to use AWS account isolation to keep your cardholder data environment apart from other workloads. Using AWS takes several requirements kind of off the table straight away. The obvious one, I guess, is physical security. You won't get physical access to AWS, even if you ask nicely. Also, no AWS services have default passwords. You do sometimes have kind of a default key, but what that means is that AWS have come up with a key specifically for you, and it's not shared with other AWS customers or indeed with your other AWS accounts. So it's not the kind of default that PCI-DSS is worried about. You do have to worry about personnel access. If staff access cardholder data as part of their normal role, you have to design for that. You don't get that for free. So that includes physical access. If you've got people, in an office or at home, and as part of their role, they have access to cardholder data, the physical access to that part of the environment is important. That's why you have the easiest time of it if you can keep the people away from data entirely. So thinking about the secure foundations, I'm going to talk about what's not mentioned here first. There's a bunch of AWS services I'm not mentioning right now in detail. Detective, Inspector, Security Hub, Audit Manager, Firewall Manager, all useful to some people. They might be useful to you as well. By themselves, these services don't let you sort of cross things off your compliance story. They help you achieve it, but they're not part of making your life easier by turning a requirement into a not applicable. So I'm not going to go into those in too much detail right now. CloudTrail does help you. It lets you provide audit logs that are tamper resistant, and I'll talk about that more later. You do have to look at those logs, so it's not a case of deploying it and leaving it. Same if you deploy guard duty. It's not enough to deploy guard duty. You have to hook it up to something so that people react when those events come through. Anyway, that's what I want to talk about in terms of foundations. And now I'm going to talk about kind of the requirements that I mentioned earlier, starting with network isolation. And this is a crucial thing where PCI-DSS has some strong opinions, and if you want to achieve an attestation of compliance or satisfy a merchant that they can confidently talk to their bank about what you're doing, you'll need to shape your architecture to match that. PCI-DSS expects you to use network segregation and a private network, so no global unicast addresses. They want to see network addresses that look like 192.168 or something, and not public addresses in your workload. You can do your own thing. You don't have to follow this part of PCI-DSS or any, but the compliance paperwork gets a lot more onerous when you deviate from the sort of the recommended obvious approach. And so to achieve this, I recommend a dedicated VPC for your cardholder environment. I'll build that up from a diagram. Now, what this diagram shows is maybe your starting point. You've got a basic serverless app, and you're thinking about how you're going to start doing card payments, and you haven't finished the design. You've sketched out a Lambda function, or four actually. 3 of them are behind an API gateway, and then there's another Lambda that actually is invoked directly. And you're using RDS serverless for persistence. Now, in this initial architecture, there's no VPC. First thing to do, actually, is make sure that you're launching this into its own AWS account. That's like the number one thing that I recommend you do. I've brought in those APIs to represent AWS services that you're using. They're your account's version of those services. For example, if you're invoking a Lambda from another Lambda, that happens by calling the Lambda API. And And like I say, you should add a VPC. So let's define that. The direct Lambda invocation is still happening. I've just cut it out the drawing to keep it simple. Some other stuff that I've not shown here, and I'm not going to draw, are multiple availability zones. You should absolutely use those for reliability, and the subnets that come with those. Just to keep the diagram simple, I'm not drawing those. But let's look at network security. So this is going to get a bit more complicated. First of all, I'd like you to look at the top of the diagram, because I've added a web application firewall. So that's outside the VPC there. I'll come back to the web application firewall. I want to emphasize that that's not running inside the VPC though. Let's look then at what's inside the VPC. So with the Lambdas running inside of VPC, I've put each of them in their own security group. This lets them separate out what they are by their function, and it lets you define rules on what traffic's allowed. So each security group can have ingress and egress rules. So to really show that you're doing things in a controlled way, you'd set ingress rules on the Aurora serverless database and on each of these VPC endpoints. More on those in a second. And you'd set egress rules on the security groups representing your Lambdas and anything else that sends traffic outbound. By default, if you don't define any rules at all, security groups don't allow traffic. So it is important to set these. Now those VPC endpoints, also called private link, are a way to represent AWS services in your VPC rather than accessing them over the internet. And that's crucial because something that you don't see here on this diagram is any internet access. Now that's not because I've left it out for simplicity. This architecture works without connecting the VPC to the internet. The reason you don't have to connect the VPC to the internet is because the API gateway is able to invoke these Lambdas directly through AWS mechanisms, and these private link endpoints allow your Lambdas to interact with other AWS services without traveling over the public internet. Now compare that with the simpler architecture that we had earlier, where what you had was that these Lambdas, when they invoke a service, and when they maybe talk to RDS serverless using the data API, when they talk to the Lambda API to invoke a different function, all that's going over, if you like, the internet. It's AWS's bit of network, but it's not inside your private controlled network, and it wouldn't match up with what a PCI-DSS auditor expected to see. So you'd have a more difficult story explaining that. You can keep the serverless properties by running your Lambdas in a VPC and using security group rules to control ingress and egress. Now on the topic of egress, you might be thinking, well, hold on a second, I actually do need to talk to something outside my network. That's pretty reasonable, you probably do. There's a bunch of ways you can do that. So here's one of them. You could define a separate Lambda, still running in your cardholder data account, that picks up tasks from a queue, that is SQS, and then having picked up a task, it calls an external HTTP API. So maybe it notifies a webhook or it's a synchronous invocation. It's the kind of thing that you can do. So the bits of your network that process cardholder data and need to be processing confidential details, you can lock them down as much as possible. But eventually, if you do need to send data outside your VPC, there are ways to do that, so it's still possible. I've talked about a bunch of concepts here that might not be familiar to everyone who does serverless, so I'm going to recap on them. Security group rules let you meet PCI-DSS requirements around a firewalling. They let you define what code can talk to what resources. Some code doesn't need any egress access, and you can make that possible, locking it down thoroughly. And you can define security group rules on VPC endpoints as well, plus your persistence resources, so RDS, DocumentDB, DynamoDB, that kind of thing. I talked about a managed API gateway. That service lets you trigger execution of code inside a VPC, even if the VPC is fully private. Within that VPC, you can use private link to access other AWS services, such as Secrets Manager. This is not a traditional packet filtering firewall architecture. Previously, in the first few years of AWS Lambda being a thing, launching inside a VPC added quite a bit of latency, and cold starts when traffic suddenly arrived to Lambda that wasn't running were a problem. Now, there is still an overhead for running in a VPC, but the story is much better. And if you were put off previously because of those cold starts, I think it's worth another look, because AWS have put a lot of engineering work into reducing that significantly. Well, there is a bit more on the API gateway story. I mentioned that there's a web application firewall in this architecture. And you can also add Lambda authorizers to apply early blocking or authenticate requests. Now that's useful because Lambda authorizers don't see the body of a request. You can still use them to check that someone's providing the right API key or make sure someone's authorized or authenticated. But because the authorizer doesn't see the request body, what that means is that you can put the sensitive data in that request body and only start processing the data when you actually reach the Lambda that's executing inside the VPC. So the architecture itself is providing security isolation. You've already minimized the attack surface by using a dedicated API gateway for card payments, and by using an API gateway full stop. And because you're only implementing minimum functionality. So inside this AWS account, I'd only expect to see card payment Lambdas, not all the other pieces of your workload. And I'm going to hope that you're following some secure coding guidelines for the code in those Lambdas. I'll talk a bit more about that later. The web application firewall on top, it provides defense in depth, and it helps you tick an important box. So you should definitely do that if you're doing PCI-DSS. Onwards now to talk about protecting cardholder data, and that's for PCI-DSS needs to be protection in transit and protection at rest. Well, for protection in transit, I'm going to guess you're already using TLS, and you should carry on. TLS is the right protocol to pick. Make sure you're using current and secure settings, so ideally TLS 1.3, TLS 1.2 at a minimum. Not much more to say there. What about encryption at rest? Well, this can be more complicated. Services like RDS let you turn on encryption at rest. Now that might be enough, and if it is, great. But you might also need something like field level encryption, where you store the card number or some other sensitive data in a particular database column, and you don't store it as is. You store that data where the application has encrypted a field, and then you write the encrypted data into the column, and the application decrypts it again. Well, if you're doing encryption like that, or various other ways, I strongly recommend that you use managed encryption. So this is where you actually call a cloud provider service to say, I've got some data, please decrypt it. On AWS, the way to do that is to choose KMS by default. It's usually the best choice, although there are others. That's the same KMS that provides the encryption for services like RDS, RDBMS encryption at rest. But you can call a KMS directly too, and the API is not that complicated. KMS is useful when you need to separate the right to encrypt something from the right to decrypt it. You've got two mechanisms available. First up, you've got IAM policies. So these are the same identity and access management policies that you might apply to roles, groups, users, S3 buckets. You can apply them to encryption keys too. So you can allow one Lambda to encrypt some data and allow only a specific other Lambda to decrypt it, if that's useful for your architecture. The second mechanism you can use is asymmetric encryption with a public and a private key. You can combine this with policy. So for example, you've got a Lambda which is allowed to ask KMS to decrypt some data using KMS's privately held copy of the key. But the public part you can share with another part of your workload, with the non-CDE bit of your app, or with a different party entirely, maybe with a bank or with the merchant. And you can also use asymmetric keys held in KMS for signing if you need to. So I'm going to show an example of that. This is more complicated than you're likely to need. I've done that to show you what's possible, not what you should do. But in this example, imagine that you need to use asymmetric RSA keys for both encryption and for signing. So as a service provider, you hold a digital certificate for each merchant that you're providing services to, and you also hold the private keys that go with that certificate. It's important to pick the right private key for the software as a service tenant that you're offering. So you don't want to mix these private keys up. And what these keys do in this example is that they let you sign messages to another party. And let's say that the reason that you're signing messages is to say, hello, I'm offering strong customer authentication here, and I'd like you to go and do strong customer authentication. You'll probably have seen this if you've gone into a bar or bought something online, and there's been a button where you can maybe arrange for the bank to send you an SMS for confirmation, that kind of thing. That's what we're talking about here. And so in this architecture, there's also like an acquirer bank. That's like the bank that the merchant's with, and the bar or whatever is going to go and say, hello, please go and find whoever issued that payment card and get it confirmed that it's definitely them. And I want that so that the risk of fraud is low. But the issuing bank doesn't just want to send an SMS whenever someone tries something. They want to know that it's a genuine request. So that's where all these signatures might come from. And then when the reply comes back to say, yep, here's proof that it's genuine, that proof is encrypted. And so to decrypt the proof, then you'd use KMS, and your workload can talk to KMS and say, hello, I'd like you to use the decryption key for such and such a bar or such and such a cafe, and I'd like you to decrypt this message and give me the decrypted version. The point is that you should get a service like KMS to do the hard work for you, and that includes key generation, making sure that access is controlled and enforced, and it covers keeping audit records as well. In fact, let's talk about audit records. What I mean really is CloudTrail. So PCI-DSS expects you to hold audit records, to track them, and to take a look at what's going on in your AWS account, well, in your cardholder environment. So there's 4 things that I'm saying will get you most of the way to compliance. And those 4 things are CloudTrail, S3 with object lock, Athena, and a notification mechanism to tell you when that there are logs to read. So in this diagram, you've configured CloudTrail. Now that's a regional service that keeps a record of everything that is done to modify things through your AWS account. I'm talking about control plane modifications, so not necessarily writing to a database, but taking a snapshot of a database, that counts. Defining a new Lambda counts. And you can, with CloudTrail, you can also set up optional extra things like I'd like to record specific accesses to an object in a bucket, or I'd like to record Lambda invocations. You can read more about CloudTrail, and I've got a link to share in a moment. Going back to what PCI-DSS asks you for, they want a daily review of audit logs. Now you can set up a filter to only include the actions that are worth reviewing. So typically that will be actions by personnel and anything unrecognized. Abnormal activity, that definitely needs reviewing. There's probably a bunch of stuff that goes on all the time that doesn't need reviewing in bulk because it is part of the normal activity of your workload. You do have to make those decisions yourselves though about at what the filtering should look like. So if this is up and running, depending on how much velocity of change you have for your workload, you might have no logs to review. For example, the CAN query might not report CI/CD changes because you've got a different audit mechanism that applies there. And so there aren't any manual changes to review, and you've got an empty list, and that's the ideal. There's nothing to review normally, and things carry on. But what you do get in this architecture is the need to show that you've got like a full set of audit logs. Separate from reviewing them daily, if someone wants to look at the logs and see that they're being kept, put them in S3 and apply object lock. So if you have a bucket default object lock configured in compliance mode, and then once those data are written, those audit logs are written to the bucket, they can't really be tampered with. And that's the property you want. You want to show your PCI-DSS auditor that the objects can't be tampered with. The great thing of using object lock is that enforcing that tamper resistance is someone else's problem. It's managed for you by Amazon Web Services. In this architecture, I've also added a log stream to CloudWatch logs. That's not the tamper-proof one, but what it means is that you can What it means is you can query that trail using CloudWatch or using Athena, whichever suits the situation you need to. As well as setting enforced retention and tamper resistance, you probably want to set a maximum retention of, say, just over a year or whatever suits your business needs, so that you're not holding data longer than you need to. Especially for compliance-oriented workloads, it is worth looking at AWS's recommended practices for setting up CloudTrail. Here's a link that I recommend you take a look at for that. Of course, reviewing every day is required for PCI-DSS, but it might not be what you want to do for security. You might want to be able to spot anomalies and react before your next daily review. And there's a service for that, of course. I'm talking about AWS Guard Duty. So you can configure this. There's not a lot of settings for it. It's a straightforward service that looks for anomalous activity. Now that could be control plane changes, the kind that you get logged to CloudTrail, or it could be network traffic and unexpected network flows that you would see if you're analyzing VPC flow logs. What's important is that you connect up Guard Duty to something like, say, Slack and PagerDuty. A typical pattern is to send most findings at any severity to a Slack channel, but no one will really read those because it's only the important findings that you're looking at, and those should go to a mechanism like PagerDuty, where you'll be much more confident that someone should react. It is up to you to respond. As I mentioned earlier, just configuring the Guard Duty service doesn't get you to compliance. You would need to show that someone's actually looking at that response if a finding occurs. For your own benefit, as well as for PCI, it's going to be useful to look at secure software development. In my view, the best step that you can take to minimize actual cybersecurity risks is around making sure people write secure code. Now, I don't just mean app code, although that is super important. Make sure that your coding guidelines and review processes clearly articulate how to define infrastructure that is secured by design. And if that's covered in your code guidelines and it's covered in your review processes, you will have a much easier time explaining to an auditor or an infrastructure reviewer why this infrastructure is suitable to hold cardholder data. Like I say, it's for a benefit for achieving compliance, but it's also a benefit directly to merchants' interests and your interests in terms of minimizing cyber risk. The next two requirements in the list after that one are about access control. Now, in my view, AWS access control takes a bit of learning, but it pays off. Whether you're authenticating end user access to an app or controlling who has access to manage the infrastructure for your workloads, you can choose to use AWS IAM principles and policies to define rights. You don't have to choose a pure AWS solution. You can link in other pieces, such as a third-party OIDC compatible service, or you can write your own custom identity provider. Now, there isn't a single pattern that's good here. It's a bit like the story with CI/CD for deploying your app and your infrastructure. You can pick a generic design, or you can choose something that matches closely what your business looks like and your needs. And deciding which of those is something that's going to be particular to your organization. There is not a one size fits all. So I'm going to recap what I've talked about, and then I'm going to detail some bits of PCI-DSS that you get to skip. I haven't talked about everything. I'll say that. Achieving full compliance, especially if you had to go for level 1 of PCI-DSS, it does take some thinking about. But you can take a serverless app and build on that existing app to achieve auditable compliance with only the complexity that you actually need. And when I'm talking about stuff that you only need, let's have some examples of actual elements of PCI-DSS that you probably don't need to deal with. First up, anti-malware. Well, you've got a serverless platform, right? If it's fully serverless, does it have any known or likely malware? Quite plausibly, it does not. If you're using a service like Aurora RDS, okay, that has instances and servers in some of its form. There is a fully serverless RDS. But that's okay because AWS are responsible for looking after their end of things there. Now, I talked about having access to cardholder data. Do your team need to access cardholder data at all to deliver the value you want? If not, you have made your compliance story much simpler. And so I strongly recommend if you can. Is your key management automated? If you've got no manual process, then you don't have to explain that the procedures are secure. Not applicable. A few more. Do your lambdas listen for insecure protocols like telnet, like a server might do, and you'd have to show that it doesn't? With a lambda, that's not applicable either. Time synchronization. It's done for you. You're on the AWS cloud. You're not running any servers where you have to manage time synchronization. Not applicable. And here's maybe a more interesting one. Critical file change detection. I think this one's more subtle and you have to take care to explain the story well here. But if you can build your app so it doesn't read from files and doesn't do file access, well then, now there are no critical files. Principles like these and the designs that I've shown so far let you take a serverless architecture, make it strengthen it and achieve PCI compliance on AWS. Thank you very much.